Okay. Let us finish our yesterday we derived for you the formula for simple pendulum, how the period change with the length, and we also derived for you an oscillating mass on a spring. Okay, so that is where we did yesterday. And then remember that the frequency, right? The frequency as you derive from this period is called a natural frequency, right? It's natural to the system. You just displace it and then you just time it, you find the period, and that is the natural frequency. Then we also go into temp oscillation. Right? I just review with you so that I can remember what is happening. Okay, we go to different type of oscillation, temp oscillation. When we say temp oscillation, we mean that there is presence of resistive force, example, air resistance. So how do we know it's damp? We see that the amplitude changes. Right? In this case, amplitude decrease gradually. Right? It takes some time for it to decrease to zero, like a simple pendulum, where you displace it, the amplitude will start to decrease until finally it is zero. Then we go to the next one. What is happening? Right? And then we say that if it's not damped, the total energy is constant because the potential change to kinetic to potential, and the oscillation will go on forever to and fro. Whereas in damped oscillation, depend on how much damping it is, the energy will decrease to zero finally. Right? The loss in energy appear as work done against your air resistance or resistive force. So the energy start to decrease. Okay, besides damping, we also have the critical damping. Right? We say if it's a free oscillation, the amplitude is the same all the time. But if it's a damped one, we displace it, then it will just come back to rest, shortest possible time in a quarter of the period. Right? No, doesn't overshoot the rest position. So that is called critical damping. That's the best because in a meter, we don't want the pointer to oscillate to and fro. We just want it to go to the value, oscillate a little bit, and come down, stop. Don't want to wait too much time to wait for it to stop and then read the meter. And then the other one is called heavy damping, right, where we displace the pendulum. Well, you can think of heavy damping as probably a vibrating mass in oil, where you take the mass up, displace it, and then you let it go. It takes a long time to come back to rest position. That's called heavy damping or over damping, right? Of no useful purposes. So today, we are going to our last part, and next week we will start with waves. Okay, we come to force oscillation and resonance. Okay, we know that if it's damped oscillation, very soon it will oscillate, and then amplitude will start to decrease, and then finally it will stop. How to keep it oscillating? We come to force oscillation and resonance, right? Just like this lady. Why is she jumping up and down on the springboard? That's called force oscillation. Right? So a force oscillation. Say again.
Isn't she moving voluntarily?
She is jumping up and down.
Yeah.
So why is she jumping up and down? Why can't just drive it, dive down? Okay, that's why you see in Olympic competition, why is she jumping up a few times and then after that dive? Right? There's a reason there.
So that to perform well.
Why? You can answer that. Why?
So that she can perform well, like give us.
Not only that, there are other reasons. Right? Since your teacher have teach you already, you should be able to answer me already. Why is she jumping like that? Not only to perform well, but there's a reason for doing that, so that she can perform well. Good. That's right, but there's a reason for doing it. Anyway, let's go to force oscillation. Occurs when a body, the body in this case is the springboard, is made to oscillate by application of periodic force. We apply a periodic force. That means you apply the force at regular interval. Periodic driving force, there's a force applied at regular interval. Right? It is a simple harmonic motion, but it's driven externally. So we can cause the springboard or the body to keep on oscillating by applying that periodic driving force. Right? And it becomes simple harmonic motion, even though there's damping. Amplitude remains constant as energy is provided by the periodic driving force. So now the periodic driving force is the one that provides the energy to the body. In this case, it's a springboard. Okay, and another example of force oscillation. Yeah. Okay, simple example of force oscillation. The child there sitting on a swing, and this one pushing it. Right? If you push one time, you'll find that very soon the swing will stop, or the amplitude will decrease until finally stop. So when the swing is displaced, right, it will oscillate to and fro with its natural frequency, like simple pendulum. So the person sitting on the swing is called the driven or the oscillating system, whereas this person is the driver. Right? It's the periodic driving force. Due to damping, amplitude of oscillation decreases. Right? You keep on pushing, the amplitude becomes larger and larger, but after a while, you find that it takes you a lot of effort to keep on pushing your brother or sister sitting on the swing. Right? But you can keep the amplitude constant because you are the one to provide the energy. Every time it comes, you push. Every time it comes, you push. Right? You must push at the right time. To keep the amplitude constant, the driver must push at the right time, that the swing is about to swing downwards. So the driver, this child pushing one, is the one who provides the energy to the swing. So why can't you keep on pushing it and the amplitude become bigger and bigger? Any idea?
No, sir.
Okay, the first thing to remember is you must push at the right time. So it means that the frequency of the driver is the same as the natural frequency of the driven. That means if you want to push a pendulum, the pendulum has its natural frequency. So the driver, you who push it, must push at the right time, must push at the frequency of the driver. Must push at the frequency of the simple pendulum. Then it will keep on oscillating with the same amplitude throughout. This is called the large amplitude. Damping or resistive forces limit the maximum amplitude. Okay, that's the reason why I asked you why you cannot keep on increasing the amplitude indefinitely. Right? When you push it, you are giving it a force, a periodic driving force, so you're increasing the velocity. And when you increase the velocity, right, as we have learned, there is air resistance. For low velocity, the damping force or air resistance is proportional to the speed. So as the speed increases, the damping force also increases. But at higher speed, is proportional to the speed square. So you can see the greater force you push, the greater speed you have, the greater the resistive force. So that's why you find that, yeah, you can keep on pushing, but you have to give more and more energy to the oscillator or the simple pendulum or the swing to keep it oscillating with larger and larger amplitude. And you become, you more or less give up because you don't have the strength to keep on pushing. Okay? So more energy needs to be provided by the driver to increase the amplitude of the oscillating system. You want to increase the amplitude, you have to push harder, more energy. But more energy, more speed, the friction or air resistance becomes larger, always opposing you. Okay, so this is acceleration, there's your motion. Right? It's going to move to the right. Resistive force to the left or air resistance to the left. You always oppose the motion and it's proportional to the speed. At higher speed, it's proportional to the speed square. That means the greater speed you give, the greater the resistive force. So more energy is required by you to increase the amplitude. So what is resonance? Right? You should have, I don't think you have download your worksheet. Right? You have your worksheet there, what is resonance, and you should be writing it up, writing in your worksheet, but I think I better tell your mother already because I think you are wasting your mother's money. You're not taking
don't tell manager, one last chance.
no chance already. I've given you 3 weeks already to download and you still haven't done.
Last won't happen again.
At resonance, the frequency of the periodic driving force equals to the natural frequency of the body being forced to oscillate. So in this case, resonance occurs when the frequency of you who is pushing the swing equals to the natural frequency of the swing. Right? Or F, the frequency of the driving force equals to the natural frequency. So in this case, the oscillator oscillates with maximum amplitude. Now you can do experiment. Okay, to investigate resonance, there's your block of wood. You can put a pointer there. There's your half meter rule. Right? We use a retortant to clamp it. There's your spring. Right? This is your 2-stretch spring. This is a vibrator. The purpose of this vibrator is to push it up and down, as the name called, right? Vibrating up and down. How do you change the frequency? You connect the vibrator to a power generator. Right? Power generator is the one that gives you alternating current at different magnitude and frequency. Then you can read the amplitude, the charges amplitude. Right? So there is your driver. There's your oscillator, oscillating mass. Right? You want to increase the damping. Right? There's this block there. You increase the area of the cupboard below. Put a cupboard below. Right? There's your cupboard. You just increase the area to increase the damping. That's all. Right? So you can change the frequency. You can read the amplitude. Okay, then you can all read yourself. And then you can change the amount of damping. Then you can plot a graph. Right? Remember, at resonance, the driving force is the one that supplies the energy to the oscillator to vibrate at maximum amplitude. The constant amplitude can also be maintained by, okay, you can push it half push, one time push, one time miss, one time push, one time miss, also can. Right? But usually we don't bother about this part lah. Right? Not that effective lah. So without any damping, the amplitude will be very large, infinity. Right? That's why you cannot push your sister or brother on the swing in a vacuum. Right? You will go to infinity. Yeah, it's very dangerous. Right? That's why I show you amplitude goes to infinity. Cannot measure it. Very large. But if there is slight damping, you will go to a maximum there. That is the natural frequency, F0 or Fn. Right? Lightly damp. Heavy damp. Right? This is heavy damp. Okay. Usually, some textbook will put resonance frequency and natural frequency the same now. Okay, I think your reference note tend to give it a smaller, the natural frequency change to smaller value lah. Okay, and then we go over that. Okay, it says alternate picture, same picture. If you are asked to sketch, okay, this one you can change the surface area, increase the surface area, increase the amount of damping. Okay, you can get it from the internet. The sharpness, right? When we say sharpness, it's this way. If light damping is very sharp, right? And then that is the natural frequency. Right? Sharpness of resonance depends on the amount of damping being sharp for light damping. For light damping, the amplitude is large. For small range of frequency, there's a small range of frequency is large. Right? Resonance frequency is middle there. Heavy damping, the amplitude of the oscillation at all frequencies reduced. Right? All the amplitude is reduced, becomes smaller. Right? They never touch, never go to zero. Right? But it decreases there. A sharp decrease. It's not more sharp. This is sharp. This is a range of frequency, right? Where it's near the resonant frequency. Okay. So for your, as I said, your note or your reference book goes to for heavy damping, it tends to natural frequency becomes smaller. Okay. Or the resonance frequency becomes smaller. That is the natural frequency. Okay. So you think you can explain to me why the driver jump up and down on the springboard?
Not sure.
Okay, what she's doing is she's trying to force the springboard, that one, to vibrate at its natural frequency. And as we have said, if it vibrates at its natural frequency, it vibrates with large amplitude. So if it's large amplitude, the springboard will push her to a higher height. So she could do more somersault before she reached the pond or the pool below. Right? That's the reason why she's doing that. Okay, this lady is Gu Lingjin of China, driving in a 3-meter springboard competition in Sydney in 2000. To force the springboard to vibrate at its natural frequency, so the diver can reach a greater height before diving. Right? There are some benefits and some troublesome resonance. In some situations, resonance can be useful, while in other cases, it can be troublesome. Right? Then we will study under sound, this one, where we can adjust this air column, and this is the one that produces the sound. So if the air column is the right height, then you will hear a loud sound. Right? So that's the benefit of musical instrument. Rely on resonance to amplify the sound produced. Or in your clock, resonance or vibration of quartz crystal are used to control clocks and watches. Right? Radio circuit also. This is a diode. This is a resonance circuit. Your coil, your inductor or coil, that's your capacitor. Okay, so this is a simple circuit to receive some radio wave. Okay, let's try worksheet there. Page 7. A tube closed at one end has a constant cross-sectional area A. Some lead shot is placed in the tube so that the tube floats vertically. This is your lead shot. This is your tube. You can use test tube if you want to. Vertically in a liquid of density. That's the density of the liquid. The total mass of the tube and its content is M. When the tube is given a small vertical displacement and then release, the vertical acceleration of the tube is related to the vertical displacement y by the expression. Okay. They have given you, they didn't ask you to derive, where g is the acceleration of the free fall. Then, as usual, they will have to ask you to define simple harmonic motion first. Right? Acceleration is proportional to displacement from a fixed point and directed towards the fixed point. Okay, then they ask you to show that the tube is performing simple harmonic motion with frequency that. So as before, right, that is what has given you acceleration proportional to displacement. Then use your definition for simple harmonic motion. And omega square equals to that constant there. Right? Compare the equation, that's what you get. And then remember that your omega is 2 pi f. Replace that as 2 pi f. Right? So it becomes 4 pi square f square. Right? This one is still the same. Then you take the 4 pi square down and then square root it. That's your answer. Anything not clear? Okay. Yep. Any problem? If not, let's carry on.
No, no problem.
On figure 4.2, figure 4.2 show the variation with time t of the vertical oscillation y of the tube in another liquid. The tube has a diameter of 2.4 cm and is floating in a liquid of density, that's the density of the liquid. Assuming the equation in B, calculate the mass of the tube and its content. So is this a damped oscillation or an undamped oscillation, or what type of oscillation is this one? What type of damping is this one? Yep. What type of damping is this
Force
one?
oscillation means will be constant. This one is damping, right?
This is a damped oscillation. What type of damping? Heavy, light, critical?
Light.
It's light, good. Light damping because amplitude decreases gradually. Good. Right? You should be able to decide from the graph itself. Anyway, you are asked to calculate the mass of the tube. Right? You have already got. So how to calculate the mass of the tube? Right? That's why you got the frequency. So how to calculate the mass of the tube?
Mass of the what?
The mass of the tube, this time, how to calculate? You have derived this formula. Now how to calculate this mass there? Yeah. How to calculate the mass? Right? A is the area, nothing given. So how to calculate the mass? Nothing given here. So how to calculate? There's the equation that you have derived. And we have just derived. So how to calculate the mass? Right? Density is given. Diameter of tube is given. Right? Diameter is given. Any idea? Yeah. How to use this equation? You can calculate the area from the diameter. Density is given. Acceleration, you can use 9.81. How to calculate f? F is not given. They'll give you only the graph. Yes. Any idea? Yep. Any idea how to calculate the frequency from the graph? Calculate the period first. Look at the graph. Where's the period? Period is the maximum there to another maximum there. Right? So the period is 0.6 seconds. Yeah. Okay. If not, you can read it from here and from here. Right? So, right? This is a time graph. So that's your period. That part there. And that part there. 0.6 seconds. Okay. That's your period. And then frequency is 1 over period. Put in your value 2 pi. Right? Area of the tube. Think of it as a cylinder. So it's pi. Right? Diameter is divided by 2. Get it radius. Right? cm, we change it to meter. Divided by 2. Square that. Density is given. Right? That's your density given. Then G is 9.81. Then M is what you want to calculate. Just play around the formula. That's what you get for M. Okay. Anything don't understand? Any question to ask? Okay. If not, means you understand. Let's carry on. State what features of figure 4.2 indicates that the oscillation are damped. Okay. What feature tell you that the oscillation is damped? Yeah, that's your figure 4.2. Yep. We answered previously now, you forgotten already. Yeah. What are the features of the graph that tell you the oscillation is damped?
Damp and light.
What features are? It's not asking you damp and light. They're not asking you that. They ask you what, how do you know, how do you decide that it's a damp oscillation from the graph?
Because it's not constant.
Amplitude decreases. What not constant? You don't answer properly. Answer properly. Amplitude decreasing with time. Decreasing gradually. So it's a light damping. Must answer the question so that your examiner can understand what you're doing. Okay. Any comment? Can write decreasing amplitude or the amplitude decreases gradually. So it's light damping. Okay. Let's try this one. A student sets up the apparatus illustrated in figure 3.1. That's your figure. In order to investigate the oscillation of a metal cube suspended spring. That's your spring. There's a metal cube. So this is a vibrator. So the idea of this vibrator is to push it in and out. So as you push it in and out, you are basically pulling the string up and down. So you're causing this metal cube to oscillate up and down. Amplitude of vibration produced by the oscillator is constant. Right? So when it tells you the amplitude is constant, it means it's undamped. It's not damped. Okay. So most likely it's light damping. The variation with frequency of the amplitude of the oscillation of the metal tube is shown in figure 3.2. Okay, so you should be able to say that's the amplitude, it's a driver, so that's the driven frequency. Resonance frequency should be able to tell that's the center, that's the largest value for amplitude. Right, let's see what they want. State the phenomenon illustrated in figure 3.2. So that's a figure 3.2. What's the phenomenon? Yeah, what do you call the phenomenon? What do you call the observation?
Damping.
Say again.
Damping.
Not damping. This is resonance. How can it be damping? It's not, you are not concentrating on the right thing. This is a resonance graph. For the maximum amplitude of vibration, state the magnitude of the amplitude and frequency. Okay, now you are supposed to read the graph. What is the maximum amplitude of vibration? And state the magnitudes of amplitude and frequency. So read the amplitude. Yeah. This A-level question, so it's a bit more straightforward. They give you free mark for learning how to read. Yep. What is the reading? Amplitude. You're going to have a problem if you don't know how to read graph. Right? They ask you the maximum amplitude, and maximum amplitude is here. This amplitude. The maximum amplitude is here. Right? 60 millimeter. Resonant frequency is here, where you have maximum amplitude. Just use the line to draw it. Okay. 16 and then 4.6. And use a line to draw it down there. The oscillation of a metal cube of mass 150 grams may be assumed to be simple harmonic motion. Use your answer in A part 2 to determine for the metal cube the maximum acceleration. How to do that? Yep. How to do that? Okay, if you're going to come for lecture without revising your notes, I think you are going to be in trouble. Right? You calculate your amplitude. Okay. Nothing else is given. So how are we going to calculate? Okay, you read the amplitude, you read the frequency. So how to calculate the maximum acceleration? Any idea? Yep. Nothing in your head because you don't revise. Right? You better do something about it. As I say, it's a waste of money to employ me to teach you. Okay, go to the definition. Right? Don't have to worry about negative sign because you are only interested in the maximum acceleration. So use A equals omega square x. Omega is 2 pi f. Right? F we have already read from the graph. So omega square that is 4 pi f. F we have already read from the graph is 4.62. And then x amplitude is in millimeter, 60 millimeter, changes to meter. Calculate out. Maximum resultant force. So how to calculate the maximum resultant force? Right? Newton's law. You got acceleration. Use Newton's second law. F equals ma. Put your mass in. Convert it to kilogram. That's your acceleration. 0.0 knot Newton. Okay. Any comment? Anything not clear? You better put effort in. As I said to you, you are wasting your parents' money. You go to university, it's even harder. Where there's no more tuition anymore. Nobody to help you. You are good, you know how to get the book, how to find the information, but the only problem with you is you don't want to learn yourself. That's why I keep on scolding you. Some very light feathers are attached to the top surface of the tube so that the feathers extend upwards beyond the vertical side of the tube. Right? Remember the oscillation? Here's the oscillation. Put feather there. Right? So the idea of feather is going to be light. It's going to increase the surface area. This is going to increase damping. The investigation is now repeated. On figure 3.2, draw a line. Right? A line means a graph lah, to show the new variation in frequency of the amplitude of vibration of frequency 2 to 10 Hertz. Right? Remember, this is damped oscillation. Line always below, right? We are increasing the damping. So the line or the curve must be below the previous line, and the peak about 4.6 or lower, right? Or slightly less and flatter. Right? That's how you draw the lines. Right? The peak there must be the same or slightly lower. That's the peak. Okay. That's what is required. Any comment?
Gotcha.
Yours, they will ask you more of memory work lah. A level is more of applying your knowledge. Okay, you can see that slightly at a lower frequency, resonant occur. Okay, I give you 5 minutes break. Then
No, Che, don't stop.
No, I don't want to carry on. I want you to go and
This
do
time
your
they don't
checkpoint.
have any time or anything.
I want you to do your checkpoint. It's a waste of time if you haven't done your checkpoint. So I don't want the video to be too long also. I want the video to stop for a while. Then you can take a short break. As it is, you are already not concentrating already. What's the point of carry on? Okay, anything else you want to ask? If not, go and do your checkpoint. If you haven't done, give you 5 minutes break to do whatever you want to do.